What will artificial intelligence solve next? Remember to like, share and subscribe. In one of the more surprising stories, it is being reported that a Jamaican maths teacher, after several group discussions on Reddit, has used the ChatGPT AI to come up with an entirely new model for the creation of life on Earth and across the wider universe. He even asked the AI to come up with a name for the theory, and it suggested it be called the Deep Earth Anaerobic Biosynthesis Theory. This model was ascertained by asking the AI to assume that the panspermia and hydrothermal vent hypothesis are both wrong. The AI's answers suggested that the emergence of biological life on a given planet is based on the intricacies of energy transference and precisely tailored mixtures of chemical elements, isotopes, and ions pushed to the planet's surface from its interior reservoirs, and not because of random falling material from space. Which also suggests that the true origin of biological life would not be linked to any primordial pool of liquids on the planet's surface, and instead it would point much deeper into the planet, even deeper than the hydrothermal vents at the bottom of the planet's oceans. In fact, this newer model points more towards the planet's mantle and the core of the planet, along with certain specific types of nuclear reactions that the planet's interior might be capable of carrying out. Which means that only the particular planets that can harness those specific resources and meet those thresholds would be able to synthesize life, and all the other planets would very much be unable to ignite the process. This is because, for the vast quantity of energy and the array of chemical resources needed for the very first synthesis of life from carbon-based compounds, only certain planetary bodies would be capable of inducing and maintaining the nuanced kinds of nuclear reactions needed for the process, as these reactions would not necessarily be of the fission or fusion reaction type. Instead, the most likely reaction types would be beta and positron decay and p-n knockout reactions. Where these are the less energy-intensive types of nuclear reactions or nuclear changes, and are observable in the processes related to PET scans or in the synthesis of fast-decaying isotopic materials for PET scan, when spent nuclear reactor rods or cyclotron particle accelerators are used. Furthermore, these are the types of nuclear changes or nuclear reactions that can be attained using mainly high-speed protons, which are basically hydrogen nuclei stripped of their electrons, rather than being overly reliant on the significantly heavier and less controllable high-speed alpha particles or helium nuclei. Consequently, within this model, the planet's core does not need to be depicted as a solid homogeneous ball of iron, nickel and cobalt, as no other layer within the planet visibly comprises of any specific element in a purely unreacted form. Additionally, given the excessively high thermal energy of the planet's deepest interior and the constant decaying of certain atomic nuclei, the planet's core should effectively be modeled to comprise of an amalgamation of many elements, all of which would be stripped of most, if not all, of their electrons and would constantly undergo isotopic changes due to the sustained frictional collisions amongst these highly energized ions or atomic nuclei. Essentially, the disposition of the Earth's structure would be modeled such that the lighter and more stable elements, mainly gases, would be oriented towards the upper crust and atmosphere, as they would take heat and excess energy away from the planet's deepest interior via convection, while the heavier and more unstable elements, mainly metals and radioactive atoms, would be oriented towards the center of the planet, due to gravity. However, even within that specific planet-wide disposition, the outer sections and interior sections of the planet would still have many light and heavy ions and elements that they share in common. Importantly, the rotational inertia of these different sections of the planet would cause the interior of the Earth to be affected by differential rotation, and this would be significant because the overall angular momentum of the crust would be different from that of the mantle, and the same would also be true for the planet's outer core versus its inner core, even though all these planetary layers would spin in the same counterclockwise direction when viewed from the North Pole. Consequently, within this model the planet's core would be represented by a swirling thermodynamic ball of electron streams and ionized plasma or naked nuclei colliding and bombarding into each other, and the somewhat synchronized movements of this amalgamation of energized charged particles would help to determine the strength and orientation of the planet's magnetic field, much like the movement of superheated plasma determines the magnetic field of the Sun. So, rather than being a uniform solid core that produces a very organized magnetic dynamo effect, the planet's core would represent a chaotic cyclotron of colliding streams of particles, churning in significantly pressurized layers. It is important to note that this new model of the orientation of the inner and outer core of the planet would not be favorable to any type of chemical reaction, as the significantly high temperatures and pressures of the planet's deepest interior would decompose any type of chemical or molecular bonds formed. However, those conditions at the planet's deepest interior would be perfect for the facilitation of many types of atomic or isotopic transmutations, which would allow some heavy unstable nuclei to forcibly be converted into neighboring isotopes of other elements, or into the standard daughter nuclei that typically form after a nuclear reaction, and the same would be true even for lighter elements such as silicon, aluminum, magnesium, sulfur, oxygen, carbon and so on. Essentially, this would result in the production of a vast quantity of loose protons or free-moving protons and neutrons, and the planet's core would effectively be awash with high-energy hydrogen nuclei bombarding or breaching into other atomic nuclei, in a very similar way to how high-energy helium or alpha particles do in the context of other types of nuclear changes or reactions. As a result of this, the convection system of the planet would inevitably bring a lot of these hydrogen ions and other isotopic material upwards, into the planet's mantle, crust, surface and atmosphere, which would cause these areas to be awash with a plethora, an abundance, or a rich mixture, of many chemical elements and isotopes that were able to become stable, and remain stable, as they move upwards and outwards away from the planet's core. Furthermore, beyond the production of hydrogen, deep within the structure of the Earth, nickel, cobalt and iron, which happen to be adjacent to each other in row 4 of the periodic table of elements, would serve as the main anchor points within the planet's core, with nickel 62 and iron 56 being the two universally most stable nuclei. Essentially, within the planet's deepest interior, most of the heavy unstable atomic nuclei that take part in radioactive decay, or other nuclear reactions, would continually undergo various changes that would steer them towards eventually becoming stable isotopes of iron, nickel or cobalt. While, for the unstable elements lighter than iron within the structure of the planet, the nuclear transmutation processes would induce the production of various isotopes of sulfur, phosphorus, silicon, aluminium and magnesium, as these metallic and non-metallic elements are all adjacent to each other, in row 3 of the periodic table of elements. Lastly, even the lighter elements such as carbon, nitrogen and oxygen would be transmuted into isotopes of each other, as these elements are adjacent to each other in row 2 of the periodic table, and their mass and atomic numbers are only one knockout reaction and a few beta or positron changes away from each other. Therefore, due to the conditions of the planet's core, any naked nuclei that receives a significant hit or strike from another naked nuclei or a high-energy particle, such as a beta or alpha particle, would inevitably have a proton or a proton-neutron pair knocked from its structure, which would result in the production of even more hydrogen and deuterium, along with even more isotopes for many of the other elements. So, it is this thermodynamic or collision-driven isotopic production chain, within the planet's interior, that would be the facilitator of the many chemical resources that further up the assembly line would be used for the synthesis of biological life, and these life synthesis or organic-type chemical reactions would immediately start to occur at the locations where the planet's structure experiences a significant reduction in thermal energy output, or a reduction in temperature, such as at the border between its molten mantle and hardened crust. Convincing evidence of this was uncovered when Russian scientists and Russian researchers presented the many signatures or hallmarks of organic and biological chemical reservoirs, entities, and structures, which were identifiable within the deepest hole ever dug on the planet. Importantly, they dug down some 7 miles into the ground, which is almost as deep as the atmosphere is thick. This was stopped in 1992, when the temperature reached 180 degrees Celsius, 356 degrees Fahrenheit, which was twice what was expected at that depth in the Soviets' mission to dig towards the Earth's mantle. Essentially, following the collapse of the Soviet Union, there was no money to fund such projects and the whole Kola superdeep borehole facility was closed down. However, while operational, an unexpectedly vast quantity of helium, hydrogen, nitrogen, and even carbon dioxide were found in pockets or cavities all along the borehole, such that the conditions at the deepest levels of the borehole seemingly match the configuration and chemical composition of the atmosphere of the Earth from some 4 billion years ago, as suggested in the Urey-Miller experiment that was designed to depict the creation of life, solely from the atmospheric conditions and compounds of the early Earth. Importantly, the main shortcomings of the Urey-Miller experiment was that 1. It focused specifically on 4 or 5 elements, 2. It only used the simplest inorganic gases that could have been formed from those specific elements as its starting point, and 3. No minerals or clays were used as a catalyst to help expedite its reactions. But, the most basic spectroscopic analysis of the sequences of compounds found in most biological entities show that these compounds are made specifically from 21 elements, and not just 4 or 5 elements. Where calcium, carbon, chlorine, cobalt, copper, fluorine, hydrogen, iodine, iron, magnesium, manganese, molybdenum, nitrogen, oxygen, phosphorus, potassium, selenium, sodium, sulfur, and zinc are regarded as the 21 elements that are essential for life. However, this number could be further reduced down to 11 if only the elements essential for the human body were being considered, or down to 6 or 5 if only the most basic amino acids, fatty acids and nucleic acids were being considered. Which means that the planet would only need to get those specific elements trapped within pockets and supplied with energy, as this would allow various combinations and permutations to form chemical bonds without immediately overheating and decomposing back to their individual inorganic or elemental components, which would allow them to remain stable long enough to undergo polymerization to become a part of even more complex chains, or to become proteins and lipids, and all of this would mark the start of the very first sign of biocoherency within the planet's structure. Furthermore, it's within these partially closed and intricately linked rock cavities or chemical loops that many of the reactants for most of the newer reactions would simply be the organic compounds, or the strings of organic chemical information, that were manufactured or synthesized in the previous reactions, only days earlier, minutes earlier, or microseconds earlier, within that same pocket, chamber or rock cavity, in the presence of certain mineral phosphates and sulfates that would serve as natural catalyst for the full gamut of organic reactions unfolding. So, the partially closed and/or interconnected reaction chambers deep within the Earth's crust that were able to successfully accelerate and sustain or prolong their synthesis of organic compounds, through the use of chemical ions, thermal energy from the planet's core, and aided by significant assistance from catalytic compounds or minerals, would in a broader sense represent the first true self-contained chemical mixtures and ecosystems of carbon-based chemical compounds on Earth, inclusive of monomers, polymers, sugars, alcohols, hydrocarbons, fatty acids, amino acids, nucleic acids, and so on. As such, within those moments, when the emergence of the first set of protein molecules are attained through those means, then this also would mark the arrival of the first set of enzymes, as well. This is because most enzymes are just proteins that, in perpetuity, attract, unlock, store or retain the chemical ingredients, reaction sequences, or catalytic pathways for ever more complex polymer chains to be synthesized or manufactured, and allow more chemical information and chemical energy to be stored for increasingly more complex chemical mixtures and chemical systems. In essence, these newly formed enzymes would be able to act as natural catalysts, or extremozyme, and thus would help many complex reactions to occur at much lower activation energy levels than they otherwise would in nature, as enzymes are known to be able to catalyze more than 5,000 biochemical reaction types, even at extreme temperatures. As such, the first emergence of life and biological complexity would not only be about the quality and quantity of chemical ingredients, but it would also be about energy availability, reaction activation levels, chemical durability, and catalytic integrity, as well. All of which would be present even as deep as 4 to 7 miles deep within the planet's crust, according to the findings of the Kola superdeep borehole located in Russia. Where, one of the more intriguing discoveries made within the Kola superdeep borehole was the detection of microscopic fossilized plankton some 4 miles down. These findings were seen as significant because usually fossils are found in mainly limestone and silica layers much closer to the surface, but these microscopic fossils were found encased in organic compounds that remained chemically stable and fully intact despite the extreme pressures and temperatures of the surrounding rocks, which ought to have thermally decomposed those compounds, specifically, back into inorganic compounds, or at least turn them into petroleum, crude oil, or hydrocarbons. Beyond this, the findings of the Kola superdeep borehole doesn't only present a new outlook on the way the Urey-Miller experiment should have been conducted, but it also confirms that the Earth's interior possesses a significantly higher level of free, or loose, hydrogen, as suggested in the model that states that the planet's core is capable of producing and performing nuclear knockout reactions, or forcing frictional collision amongst naked atomic nuclei, and inducing isotopic decay. This is because another unexpected discovery, at various stages, within the Kola superdeep borehole expedition was the large quantities of hydrogen gas that escaped as they dug the hole. The drilling mud that flowed out of the hole was described as boiling with hydrogen. However, this should not have been the case, as most of the accepted models, regarding the overall structural formation of the planet, point to the notion that most, if not all, of the planet's hydrogen should have evaporated away into space when the planet was super hot, was being bombarded by meteors and asteroids, or was in a fully molten state, billions of years ago. So, the findings from the Kola superdeep borehole points to the possibility that the planet most likely has a natural geothermal, or thermodynamic, mechanism, deep within its interior, that has somehow produced an excessive amount of freed hydrogen atoms and/or isotopes. Because what are hydrogen atoms if not just individual protons, or proton-neutron pairs, that regain some electrons to become stable atoms? Consequently, it is only at those depths that are comparable to the superdeep borehole where there would be enough energy, along with pockets or cavities filled with the many gaseous atoms, ions and isotopes, especially of hydrogen, that would be needed for the emergence of the first set of simple enzymes, or natural organic catalyst, that would facilitate the creation of the very first closed-loop autocatalytic chemical mixtures. Such that, these chemical mixtures or chemical systems would conduct organic chain reactions on overdrive, as the chemicals contained within them would be either the main ingredients and/or the means of lowering the activation energy for future reactions, which would exponentially increase the likelihood of specific types of reactions taking place, or being directed to converge or diverge in particular ways. Essentially, these mixtures would contain both the reactant and catalysts that were synthesized by and/or within the mixture itself, as enzymes are the type of organic compounds or polymers that can catalyze the production of other organic molecules. Additionally, the existence of these catalyst-filled mixtures that are running on reaction autopilot would facilitate, or allow, ever more complex polymer chains to be synthesized, or manufactured, within minutes if not microseconds after each other, which would make them appear almost as if they were organic chain reactions. Importantly, this would allow vast quantities of chemical information, or chemical energy, to be stored within these increasingly complex compounds, or chemical systems. Therefore, the constituent parts, or catalytic substances and substrates within these dynamic mixtures would quickly evolve to create or synthesize more complex and larger polymer structures, which would allow them to acquire more functionalities, as well as more physical properties, traits, and shapes. After that, the first set of organic molecules, or polymers, with the catalytic properties to attract, optimize, recall and/or preserve the exact steps, ingredients, and/or components needed for the production of special and/or complex organic compounds, such as proteins, would serve as the first type of genetic code, and would serve as a means of storing the chemical and catalytic identity of the mixture that they are enclosed in. In addition to this, the emergence of lipids, which are the complex polymer chains, or molecular chains, of fatty acids, would represent the emergence of the very first partially insoluble molecular shells or membranes, that could enclose or wall off parts of these mixtures, which would allow some catalytic systems to develop new and/or unique identities, as they begin to make or synthesize new compounds, even while being in the same solution or same pockets as others. Thus, the many little insoluble spherical pockets or oily bubbles created by these lipid molecular shells would serve as the very first maze-like multi-chambered, or multi-layered, miniature structures that could fully enclose and insulate various chemical systems, or mixtures, of ongoing molecular reactions, and strategically allow them to maintain their separation from all other ongoing reactions involving other catalytic enzymes and proteins, or from all outside or environmental stimuli. Consequently, the concurrent emergence of the carbon-containing compounds, or chemicals, known as proteins, enzymes, and lipids, along with any means of molecular chemical information storage, would mark the point where some of these organic molecular systems would represent fully functional sequences, or pockets of chemical information, and they would preserve the accumulated lineage of the chemical information, properties, functionalities, chemical pathways, rules, protocols, syntax and/or chemical signatures, unique to the systems or mixtures that they came from. As such, these new and/or ever-changing units or pockets of biological and chemical coherency would exist ostensibly as an enclosed set of localized mixtures, or as a web of compounds, that exist collectively to follow an existential set of chemical rules, written in and/or stored in carbon-based compounds. Therefore, within these now lipid-enclosed chemical pockets, reactions that once took days, or even millions of years to unfold within deep underground natural cavities, would now reach completion within microseconds, and this jump in complexity and efficiency would result in the creation of ever more complex chemical entities, using strictly energy from the planet's interior, and these new systems, mixtures or floating pockets of organic chemical compounds or polymers would directly straddle the line between the living and non-living world.